Welcome students. Today we are going to talk about another important device or an accelerator which is known as the cyclotron. It is a simple device, yet it is very important as far as particle accelerators are concerned. So let's see what a cyclotron is. So it's a device, as we have already discussed, which is used to accelerate charged particles or ions to high energies. So basically almost all accelerators, they work on the principle that charged particles are affected by electric or magnetic fields. So this is another device in which we accelerate charged particles to high energies. It was invented by E.O. Lawrence and M.S. Livingstone in the year 1930. Since then, a lot of advancement has been done in accelerator technology, and the cyclotrons also have evolved over the years. So, as we have been talking about, even in a cyclotron, a combination of an electric and magnetic field is used to accelerate particles, and the path followed by the particles inside a cyclotron or in a cyclotron as they are being accelerated is cyclic in nature, circular path, hence the name cyclotron. So this is a picture of a cyclotron. So when we draw it in the blackboard or we draw it in our copies, we can draw a small schematic figure, but actually the sizes of the operational cyclotrons are not that small. So this will give you an idea about the size of a cyclotron. Now let's go ahead. What is the basic principle behind the operation of a cyclotron? So it is based on the principle that charged particles are affected by electric and magnetic fields. So we have been stressing on this point that this basic principle of the effect of electric and magnetic fields on charged particles makes possible most of the accelerators. We discussed about the linear accelerator. There also we apply a small oscillating electric field to accelerate particles. Same as in the case of the cyclotron, here also we use an electric field in combination with a magnetic field for accelerating particles. So this forms the basic principle of operation of a cyclotron. So the charged particles are accelerated by applying an alternating electric field. And the particles, they move in spiral paths due to a magnetic field applied perpendicular to the path of the particles. So what it means, basically we are talking about the force experienced by a charged particle when they move in a magnetic field. So usually the force exerted by the magnetic field of strength B, let me say, on a charged particle of charge Q is given by QV cross of B, or it's QVB sine of theta, the Lorentz force, where theta is the angle between the direction of the velocity vector and the magnetic field. So if the magnetic field is applied perpendicular to the path of the particles, the force experienced by the charged particle because of the magnetic field will be perpendicular to the velocity vector, and hence because of a magnetic field the particles, they follow a curved path. So that is what happens in a cyclotron. The cyclic paths are there for the particles, and the magnetic field is applied perpendicular to the path of the particles. How it is done, we'll see when we talk about the construction part. So the particle experiences the alternating field multiple number of times, getting accelerated in steps. So what it means is we apply a comparatively small alternating electric field and the particles are allowed to accelerate through the field or due to the field number of times. It's not that we are applying a very strong or high voltage to the particle. We are applying a small voltage, but we apply it number of times. So every time the particle experiences the field, it gets accelerated. So in steps, it gets accelerated. So how it is achieved, we can see when we talk about the construction and operation of the cyclotron. So these are two figures which will show you the construction of the cyclotron. So just one second. Okay, here we have basically a cyclotron. It has two semicircular hollow metallic electrodes called the Dees. So these are the two Ds we are talking about. This is one D and this is the other D. These are metallic electrodes which are hollow inside. So the semicircular Ds, because of the shape, we call them the Ds. And the particles, they move in circular paths inside the Ds. So this is hollow inside, you should be able to make out. And these are the two electromagnets which gives rise to a magnetic field perpendicular to the path of the particles. That means the path of the particles is nothing but within the Ds. So we can say the magnetic field is perpendicular to the plane of the Ds. So this is from the side view. So you can see the spiral paths. The source of the particle is somewhere at the center. We'll talk about it more. But basically what is being done is between the two Ds an oscillating electric field is applied. So if you see the top view, it looks something like this. The source of the particle is somewhere near the center of the D, and between the two a oscillating electric field is applied. So the particles moves within these in spiral paths. What actually happens, and the whole assembly is kept inside a evacuated or an evacuated chamber. So as I was talking about, this I am putting it in words. High frequency electric field is applied between the Ds. The strong magnetic field perpendicular to the plane of the Ds that makes the particle go round and round in circular paths inside the Ds because of the strong magnetic field. And another point to note here is, I have put it down in words in the later slides, but here itself I am talking about when the particle is inside the D, this is a metallic chamber. So from electrostatics we know that a charged particle or inside an electric chamber or inside a metallic chamber, the electric field is zero. So the particle does not experience any electric field when it is inside the electrode. Only place where it experiences the field is between the two Ds, in the gap between the two Ds. So the entire setup is kept inside an evacuated chamber. Now, the charged particles or ions are released near the center of the Ds. This is the source of the ions. So what happens once the particle is released? Let me say I'm releasing a positively charged particle at this point. So at that point, let me say this D. So this is alternating electric field, means the Ds, they change polarity. This is positive, then after one half cycle, this becomes positive, then another half cycle, this becomes positive, and so on. The polarity of these two Ds, they keep on alternating, changing. So I release the particle here. Suppose it's a positively charged particle, and at that moment this is negative. So what will happen? The particle will accelerate across the gap and it will attain a finite acceleration. It will enter the D with a finite velocity. But inside the D, what happens? The particle does not experience any more electric field. So what it will experience? It will experience only the magnetic field. So because of the magnetic field, the particle goes round the circular path and it reaches the gap again. So inside the Ds, they don't experience any electric field. So path inside the D is circular due to the influence of the magnetic field. It goes around a circular path. And the particle, it takes a finite time to travel through this circular path. Semicircular path, you can say. Takes a finite time because it has finite velocity. So what is done in the cyclotron is, if the time taken is equal to the time of half cycle of the applied AC, the polarity changes at this moment. That means if the time taken by the particle to travel in a semicircular path is exactly equal to half the time period of this AC, then what will happen? At the moment the particle reaches the gap, the polarity changes. So this becomes negative now. So the particle will be accelerated across the gap. So what will happen? The particle will gain velocity again. So it enters this D with higher velocity. Now we know the radius of the circular path followed by a charged particle in a magnetic field is proportional to its velocity. So we'll see that when we talk about the theory. The radius of the circular path for a particle in a magnetic field is proportional to its velocity. So it enters this D, it accelerates and it enters this D with higher velocity. So the radius of curvature of this semicircular path is more than this. But then what happens? Its velocity also is higher. So it takes the same time to travel this path as it took to travel this path. Right? So the radius of the path will be more, hence the particle takes the same time again to travel through the D. For this path, radius is less, velocity is less. For this path, radius is more, velocity also is more. So it takes the same time to travel through the semicircular path in this D. So again when it reaches here, the polarity changes. Again the particle accelerates across this gap. So that is the synchronization condition. So the condition is that for each circular path, the time taken by the particle to travel through this semicircular path is equal to half the time of this applied AC. So every time the particle reaches the gap, the polarity changes. So the process continues and the particles keep on accelerating across the gaps and keep on traveling paths of higher and higher radius. So particle accelerates at each passes across the gap and the radius of the circular path keeps increasing with each step of acceleration. When the final desired energy is attained, the particle is deflected out of the D to hit the target. So when you are sure that it has gone round many semicircular paths going round and round, it has attained its velocity. So what will be done? You apply a small voltage and deflect the particle from its path. It will come out of the cyclotron and hit the target. So the theory we have to talk about. The theory is we have to develop a theory. Basically, the theory means we have to find out the synchronization condition. What should be the frequency of the applied AC so that the synchronization is achieved in the cyclotron. So it's based on the force experienced by charged particles in electric and magnetic fields. I'll go a bit fast through this part. The force experienced by the charged particle in the magnetic field is QVB. It's QV cross of B rather, where cross is the cross product. So V cross B means VB sine of theta, but theta it's 90 degree because we are applying the magnetic field perpendicular to V. So it becomes QVB. So this force acts perpendicular to the path of the particle and makes the particle move in a circular path. Right. So any particle moving in a circular path of mass m and velocity v, the centripetal force is given by mv squared by r. So what is generating the centripetal force? It's the force due to the magnetic field. So mv squared by r is equal to qvb. Or from this expression we can find out an expression for the radius of the circular path. You see here m is the mass of the particle, q is the charge of the particle, b is the externally applied magnetic field. So if M, Q and B are constant, you can see that the radius of curvature is proportional to the velocity of the particle, other parameters remaining the same. So as the particles gain energy, that is, as velocity increases, the ions move in paths of larger and larger radius, obviously. So the path of the ions in the Dees is spiral, semicircular basically. So it's going like this, higher radius, it spirals round with increasing radii. Now the time taken by a particle to complete a semicircular path inside the D is given by T is equal to half 2 pi by omega, that is pi r by v. Straightforward, we can write it without this step also. Semicircular path, total circumference for a circular path is twice pi r. So semicircular path is pi r. Pi r by v gives me the time taken by the particle to complete a semicircular path inside the D. Or here we are talking about the total angle 360 degrees twice pi, and omega is the angular velocity. Half of that is the time taken to complete a semicircular path. So putting R is equal to mv by qb that we found out earlier, we get T is equal to pi m by bq or qb, where T is the time taken by the particle to go round the semicircular path. So the time taken to complete a full circular path will be twice of T. So that is twice pi m by bq. That is the total time taken by the particle to complete a full circular path. This shows that the time taken by the particles to travel a circular path inside the Ds is independent of the velocity of the particle and radius of the circular path. We can see from here, T is independent of velocity and independent of radius. So if I have a particle of mass m which is constant, charge q which is constant, we apply a constant magnetic field. That means the time taken by the particle, irrespective of the circular path inside the D, irrespective of the radius, irrespective of the velocity of the particle, T is fixed. So this makes possible a cyclotron. As the particles, they take the same time to travel the circular paths irrespective of their radii. So the condition for keeping the particles in phase with the external field is the frequency of the particle is 1 by T, it's bq by 2 pi m. This value of frequency of the particle is called the cyclotron frequency. And for synchronization, for making possible a cyclotron, to make possible the condition that whenever the particle reaches the gap, these they change polarity. That condition can be achieved if the frequency of the applied AC is made equal to this frequency. So this frequency given by bq by 2 pi m is called the cyclotron frequency. And the applied AC or the applied electric field should also have this frequency. So if that condition is satisfied, the cyclotron is possible. So the particles will be in step with the applied AC. So what about the maximum energy attainable in a cyclotron? So maximum energy attainable is dependent on the maximum velocity, of course. When we talk about energy in any accelerator, we talk about the kinetic energy. So kinetic energy is dependent on the velocity. So the maximum energy attainable is of course dependent upon the maximum velocity. Now we know velocity and radius was proportional to velocity. So the maximum velocity again will be proportional to the radius of the last orbit and hence the radius of the D. Means the maximum velocity that can be attained in a cyclotron, it depends upon the size of the D. That is the maximum radius that the particles can have inside the D. So if R is equal to R maximum is the radius of the last orbit, and V maximum is the maximum velocity of the ions in the last orbit, then we have V max is equal to BQR by V. This is using the expression for velocity that we found earlier. So the maximum kinetic energy of the particle is half mv square, V max square. So putting the value of V, it is half B square Q square R square by m. So literally, the maximum energy is dependent on B and R. Higher the value of B, we have more energy, but B increasing the magnetic field, there is a limit to it. You can't keep on going increasing the magnetic field. It's difficult to deal with strong magnetic fields. So one possible way is to increase the radius of the Dees, but we can't go on increasing the radius of the Dees because the size becomes too large. So there are some limitations to a cyclotron. So we have to see what are the advantages and limitations. So comparatively smaller in size compared to the other accelerators, compared to the LINAC that we talked about in the last class. And we can use low voltage. We don't need a very high source of voltage. Low voltage having a peak value of 10 to 50 kilovolt can be used. However, cyclotron is comparatively much costlier. Also, when the energy of the particle increases, that is, the velocity of the particle increases at particular limits, what happens? Relativistic effects come into picture. The velocities become relativistic, so the mass of the particles becomes relativistic. Now we know at higher velocities there is an apparent increase in the mass of the particles. The particles becomes massive, relativistic mass. So what will happen? The cyclotron frequency, we have mass in the denominator here. So once m becomes relativistic, the particle attains very high speeds, m starts increasing. So the frequency of the particles starts decreasing from this value. So the condition was we made the frequency of the AC to be equal to this frequency. So what happens? The particle frequency starts decreasing compared to the applied AC frequency. So the particle starts falling off step. That means before the particle reaches the gap, what will happen? They change polarity. So the particle loses its synchronization with the externally applied field, and there can be no more effective acceleration of the particle beyond a particular limit. So this is a major limitation to a cyclotron. Also, this is the reason why we can't use cyclotrons to accelerate electrons or lighter particles effectively to very high energies. Why? Because they attain relativistic speeds very soon, lighter particles. So what is the way out of this? One way is, as m starts increasing, we can increase b, right? So this is one way of overcoming this limitation. As m starts increasing, b also is increased so that f remains the same. Other way around, as m starts increasing, f starts decreasing, the frequency starts decreasing, so we can keep on decreasing the frequency of the externally applied AC. So these are two ways in which the limitations of a cyclotron can be removed, and these are used to design, these two ways are used to design some other accelerators in which this limitation of the cyclotron is removed. We'll talk about them later. So that is all about cyclotrons. So thank you.